Hello and welcome back to Let's Code Physics. Last time we successfully corralled our electrons into a wire so that they had some boundaries to bounce off of, and we got a little bit better picture of what current looks like in a wire. Of course, if we're going to make a circuit, we're going to need to have many wires. We're going to have them connecting and splitting off and joining back together and all this stuff. So the first thing we're going to have to do, and that we'll work on today, is just keeping track of multiple wires in our code. So what I've done is, last time we made this class wire. Everything up above the red line here is the same as it was before. The wire has a direction associated with it. It has a width and a length. We assign it a top, bottom, right, and left bounds, and we give it a resistivity. This time, since we're going to have wires of different resistivity, we are going to move the scattering time into the wire definition. So scattering time is the average amount of time that an electron can go without encountering a collision. So it's the average time until the electron gets scattered. So this is an intrinsic property of the wire, depending on what it's made of and how the atoms are arranged. It goes like the inverse of the resistivity. So there's some other stuff that goes in here, like the electron charge and electron mass and things like that. But just for the sake of visualization, we're going to make this 1 over the resistivity. So we've moved scattering time out from the electron class and into the wire class. What we're also going to do is we want to compare different wires, and so we're going to be recording the average position of the electrons within each wire. So for today, we're going to work with two different wires. We're going to have one running up here, one running down here. They won't touch, they won't cross, they'll have their own electrons. So it'll be just like in an experiment when you are measuring Ohm's law for two different resistors, basically. And so what we have to do now is when we are scattering the electrons, instead of it just being the electron scattering time, it's got to be that wire scattering time. So we're also keeping track of, for the electrons, which wire they are in. So we've defined this additional piece here, this electron.inWire property, which just keeps track of which wire the electron is in. So we've got the same scattering process that we had before, the same process of bouncing off the walls, only again now we're looking at wire list of whichever wire the electron is in. This is going to be really helpful notation next video when we start to connect our wires and our electrons can go back and forth from one wire to the next. Down here we're keeping track of the average position of the electrons within each wire. So we've got an average position for wire 0, an average position for wire 1, and we're going to graph those separately to get an idea of how the current changes with the resistivity. Here we've got our wires being defined, so we're keeping track of those in wire list. So they're both going to be centered horizontally on the screen. One's just going to be 2 units below the other one, and that one on the bottom is going to have right now twice the resistivity of the one on the top. When we go to create our electrons, we now need to keep track of which wire they're in. So you notice that half of the electrons are going to be at y equals 0, that's in the top wire. Half of them are going to be at y equals 2, that's in the bottom wire. And what we need to do then is we need to tell them which wire they're in. So right now I'm manually telling the electrons which wire they're in. In the next episode, when we have wires going back, we have electrons going back and forth between wires, then we'll need to be able to automatically determine which wire a given electron is in. And as always, we've got our electric field here. We're going to have the same electric field for the two wires. We'll need to make some way of having the electric field be different in the wires, just because we've got things going in parallel. They won't necessarily have the same, actually if they're in parallel, they'll have the same voltage but different currents. In series, they'll have the same current but different voltages. So I'll need to figure out a way to make this unique to different wires. Right now we'll just keep it as the same between the two wires though. Okay, everything else pretty much runs the same way. We've got our move electron subroutine being called here. It's returning to us the 2 average X positions, one for wire 0 and one for wire 1, which we're going to keep track of and graph. So first, let's check the animation to make sure that our electrons are doing what we expect. Okay, so we've got our wire 1 up here, our wire 2 down here. We've got, I think it's 30 electrons in each one. They've both got an electric field pointing to the right, so these electrons are going to tend to go to the right. Except what you notice right away is that the electrons in the top wire are heading over to the right a lot faster than the electrons in the bottom wire. The difference there is the resistivity. So because this one has a lower resistivity, it has a higher scattering time, so electrons are able to travel farther in between collisions, so that by now most of them are clustered around the right-hand side. Whereas this bar has twice the resistivity of the top one, and so it has a lower scattering time, meaning the electrons encounter collisions much more frequently. You can even see they are jostling around a whole lot more than the ones up here are. These are getting to travel in a straight line a lot more of the time than the ones down here are. I mean, we've still only got, about a third of them clustered in this section of the, two-thirds of them clustered in this section of the bar, whereas most of the ones in this wire are clustered in the rightmost third. We can see that we can see the resistivity come to play in the graph. So again, this is the average X position. So the top one's in green, the bottom one's in red. We have a green wire and a red wire. We will not be cutting any of them. So we've got here, we've got a slope, a pretty regular slope like we've been seeing before, and then it levels off as they start to bounce against the rightmost edge. For the red one, we've again got a relatively consistent slope, and then it starts to level off as well. So they both eventually level off, but the green one gets there a lot faster than the red one does. So if you compare this slope to this slope, you notice that those are rather different quantities. Let's see if we can get a more numerical idea of what that slope is. So let's have these electrons start at 0. And let's actually make these wires a little bit wider. Let's have them go, let's have them be 20 long, and then let's have them be centered a little bit to the right. So we'll go with, let's see, yeah, I can make these centered 5 to the right, and those electrons will still be in the wires. So all of my electrons are going to start out at 0, so that average will start out at 0 this time. All right, cool. So we moved our wires over a little bit. So this is giving our electrons, basically what we're doing is we're giving our electrons farther to travel over to the right, coming this way. There's an action perspective. And so what I expect to see is a drastically different slope for the green than for the red. And of course, they track for a little bit here, then the red gets knocked back a little bit, the green continues on ahead. So if we take a look at the slope overall, so we started at 0, 0, so that's pretty easy, makes it pretty easy to calculate the slope. So for example, right here, we've got, let's call that 170 over 3. So let me get out my calculator. I've got a 170 divided by 3. So the green one has a slope of about 57. The red one's got a slope of about 200 divided by 2.5. 200 divided by 2.5. We get a slope of 80. Oh, I did that opposite again. I need to rise over run, Brian. Rise over run. All right, so 3 divided by 170 is a slope of 0.0176. And then rise over run, 2.5 divided by 200 is 0.0125. So we've got a pretty noticeably different slope there once I actually calculate slope using the way you're supposed to. Rise over run. Let's see. Let's try one more, and then we've got more data points. So here I've got 6 divided by 400. Gonna do it the right way this time. 6 divided by 400 is about a 0.015, so it leveled off a little bit. And here, let's see, we did it at the 400 mark. So let's try to get the 400 mark and 4.2. So we'll say 4.2 over 400. So we go to about 0.01. So we've gone from 0.015 to 0.01. So that is a decrease of 0.005. That's how much they decreased by. divided by the original 0.015. So that caused a 33% reduction in the current. And of course now this one's leveling off a bit. This one's leveling off as well because they are starting to reach the rightmost edge there. So doubling the resistivity caused our velocity, which is roughly the current, to decrease by about 33%. So that gives you an idea of the power of resistivity in materials science, because materials science can tell you what the resistivity is based on modeling what the wire is made of. Cool, so this has been a pretty big success. We'll end with a close-up of the electrons coming to the end of the wire there. Next time we will try connecting these wires and see what we need to do to get electrons to move from one wire to the next. And because once we have connected wires, we can get a loop, and once we have a loop, we have a working circuit. And that's got me very excited. All right, thank you so much for watching. I will see you next time. Bye-bye. Hey everybody, thanks for watching today's video. I just wanted to conclude with a quick plug for one of my favorite podcasts, They See Me Rollin'. I checked on my podcast app and that title does not include the G. So when you go search for it, that is They See Me Rollin', not rolling. I think that helps clarify some confusion when you go search for it. Anyway, this is an actual play Dungeons & Dragons podcast that is incredibly entertaining. They are wonderful storytellers, wonderful improv actors, and they're going through this very creative, very imaginative, very vivid fantasy setting. And one of the nice things that they do is that in the editing process, they edit out all of the rule discussions, the rolling, the math, etc. Not that I don't enjoy podcasts that include that, but it just creates this environment that focuses more on the narrative than on the game mechanics. So if you like fantasy stories, if you like Dungeons & Dragons, if you like any kind of tabletop RPG, if you just like listening to guys saying goofy things in a fantasy context on a podcast, go check them out. Again, that's They See Me Rollin'. Thanks so much for watching, and I'll see you next time. Bye-bye.